So hi, I'm Mark and I'll be taking you through the topic of exponentials and logarithms, but you'll also be seeing me later in this course as well. So in this lesson, we'll be looking, as I mentioned, at exponentials and logarithms. However, firstly, we're going to be looking at indices in baseball and what did they have in common. So as we can see in the imagery, there are bases, and these are quite important when working with indices and logarithms, particularly when we want to simplify these expressions and then eventually solve and sketch their equations. In this lesson, we'll be looking at a review of index laws. So these index laws will be something that you may have remembered from junior year's mathematics, but also Unit 1 and 2. So in this particular lesson, we're going to be looking at a review of these laws, as well as rational indices and negative powers. So looking at our index laws, there are 5, with the 5th one being the 0th power. So sometimes you'll see 1 to 4 and then the 0th power. But to review each of these, index law 1 and 2 refer to the multiplication and division of indices. Index law 3 and 4 refer to taking an index to the power and then division using the index. So looking at index law 1 and 2, we can see that when we multiply indices of the same base, we add their powers. When we divide indices of the same base, we subtract their powers. And that makes sense because when we multiply two indices of the same base, we add their powers. So the opposite of multiplication is division, and the opposite of addition is subtraction. Looking at index law 3, this is a little bit different now, and we have a to the power of m to the power of n. So when you have brackets involved, this is a little bit different to when we're just multiplying two indices of the same base. This is where we actually multiply the powers. And this is because we're taking essentially the power of an indice already. Looking at index law 4, we've got a divided by b to the power of n. So when we have a fraction to the power of n, we're again raising each part of the fraction, so the numerator and the denominator, to that power of n as well. And finally, the 0th power, anything to the power of 0 equals 1. Some of the key terms that we need to refer to are index and power, so the power that a number is raised to, a base, the value that is multiplied by that power. In index law 1, for example, the base is a, and it's being raised to the power of m. So in this worked example, we're going to be looking at simplifying the expressions using a combination of these index laws that we've just reviewed. So we've got 2x cubed y all squared. So again, because it's all squared, we are going to raise each of those bases on the inside to the power of 2. So we're going to have 2 squared, then x to the power of 3 times 2. So 2 squared came about because technically that's 2 to the power of 1. 1 times 2 just gives you 2. So 2 squared, x to the power of 3 times 2, y to the power of 2. So 2 squared, we can evaluate that. That becomes 4. So we'd have 4 x to the power of 6, y to the power of 2. So that's as simplified as we can go in this particular instance. Looking at part B, so we have 2x cubed y squared divided by 5x to the power of 5 times 4x squared y cubed. So there are multiple ways, particularly when you have algebraic fractions, when you multiply or divide them. You can either simplify each side first, or you can do the multiplication and division first, whichever you're more comfortable with. In this instance, I'm going to multiply first. So we're going to have 2 times 4, then x cubed plus 2, because again, it's x squared on the other numerator, y squared, because there's no other y, all divided by 5x to the power of 5, y cubed. Yeah, we've got some space. Let's bring it up here. Why not? So now 2 times 4 gives you 8. So we have 8x to the power of 5 y squared divided by 5x to the power of 5 y cubed. So x to the power of 5, when we're dividing dividing those of the same base. So x to the power of 5 divided by x to the power of 5 is simply x to the power of 5 minus 5. So that's going to give us 0. So in other words, just 1. So we're going to have 8 times 1 is just 8. Then y squared divided by y cubed. over 5y cubed. Again, we can't simplify 8 divided by 5, so leave the fraction as it is in this instance. Then y to the power of 2 divided by y to the power of 3. So it's y to the power of 2 minus 3. However, we're going to have a negative power. So we've got 8y squared divided by 5y cubed. So we're going to leave it in that form in this case with the 8 and the 5 because we can't simplify that any further. However, we can simplify the y squared and the y cubed. Thinking about positive indices, which we're going to get to later in this session, but the y squared and the y cubed, when we divide indices, we're going to subtract their powers. So y to the power of 2 minus y to the power of 3. That's just going to become 8y to the power of 2 minus 3 all over 5. And that becomes 8y to the power of negative 1 divided by 5. To rewrite that as a positive index, we obviously want to have y to be to the power of positive 1. So to do that, we simply move it to the denominator. So this would become 8 divided by 5y. You probably don't need that second last step. However, if you're not necessarily comfortable with your index laws at this point in time, it's definitely worthwhile showing all of your working out where necessary. So rational indices and negative powers. So looking at rational indices, we can see we have the example of 4, or the quartic root of x cubed. We can rewrite that as x to the power of 3 over 4, or 3/4. And the nth root of a value is in the denominator of the rational index and the power is in the numerator. And we can see this because we have the quartic root. So that's the nth root, if you like. That's going to be in the denominator of the fraction. And then what x is being raised to the power of on the inside of that root is 3. So 3 would go in our numerator. And if we look at the proof of this particular rule, if you like, or index law. So if we look at a proof of this index law, so let's say, for example, we had m, or the mth root of a to the power of n. So this could be rewritten, as we know the mth root, or if we think of the square root, that's simply a to the power of a half. So we could say that a to the power of n has been raised to the power of 1 over m. And then multiplying these two powers, so this is equal to a to the power of n times 1 over m, which is equal to a to the power of n on m. So that's where that proof of rational indices and that index law comes from. So now looking at negative powers, sort of similar scenario in this instance. So let's say, for example, we had a to the power of 0 divided by a to the power of m. This is equivalent to a to the power of 0 minus m. So, and what we can see is, well, a to the power of 0 is simply 1. So if we replace that with 1 divided by a to the power of m, this is going to equal, on the right-hand side, a to the power of a negative m. And we could rewrite 1 divided by a to the m as a fraction. So 1 divided by a to the m equals a to the power of a negative m. So just a really nice proof of negative powers. So again, we're going to be looking at simplifying expressions using a range of index laws, and in particular, we're going to have to then write that as a positive index, and we can see we've also got a square or a root as well in this particular example. So what we know from the previous line is that when we have a root, we're going to write that using a rational power. So we're going to have 8x squared y cubed to the power of negative 1 over 3 times 2y divided by x to the power of negative 1. So then we're looking at 8 to the power of negative 1 over 3, x to the power of negative 2 over 3, y to the power of negative 1, times 2y on x to the power of negative 1. So putting this all together with the negative index, we can rewrite these all using the positive index first, if you like. So all of the top line, all of that left-hand side, so the 8 to the power of negative 1 over 3, x to the power of negative 2 over 3, and y to the power of negative 1, we can write on the denominator of a fraction. So we go 1 divided by 8 to the power of 1 over 3, x to the power of 2 over 3, and y times 2y. And that x to the power of negative 1, I'm going to bring to the numerator of that fraction. So it's going to be times 2yx. So now this would become 2yx over, and if we look at the cubed root of 8, the cubed root of 8 we can actually evaluate, and that happens to be 2. So it becomes 2x to the power of 2 over 3y. Let's jump up here. So 2 divided by 2 simplifies to 1. So we're going to have yx, this would equal yx on x to the power of 2 over 3y. The y's will cancel out. So cancelling out the y's, we're going to be left with x divided by x to the power of 2 over 3. So now having this fraction, we have, that's x to the power of 1 minus 2/3. 1 minus 2/3 simplifies to 1/3. So we're left with x to the power of 1 over 3 as our final answer. Okay, so in this mega question activity, we have 2 squared times 3 all squared divided by 27 to the power of 1 over 3. So 2 squared times 3 all squared divided by 27 to the power of 1 over 3 happens to equal 48. So let's look at the left-hand side first. So 2 squared times 3 all squared. 2 squared is 4, so we're going to have 4 times 3 squared divided by 27 to the power of 1 over 3, so essentially the cubed root of 27. 4 times 3 is 12, so 12 squared divided by the cubed root of 27. Cubed root of 27 number multiplied by itself 3 times happens to give you 27, so we've got 3 times 3 is 9, times 3 is 27. So the cubed root of 27 is 3. So we're going to have 12 squared divided by 3. 12 squared is 144. Divided by 3, and finally 144 divided by 3 equals 48. So the answer is C. To summarize this lesson, looking at the review of the index laws, so we've got 5 index laws, the 5th one being the 0th power. We also look at rational powers and negative powers as well. So in the next session, we're going to be looking at solving exponential equations and using all of these laws in combination with one another to help us solve exponential equations. So in this lesson, we'll be looking at exponential equations. Before we get stuck into this lesson, let's have a look at this particular image of this person in a laboratory. So why and how does this have anything to do with exponential equations? Well, if we think about the word exponential, so that exponential growth or decay, growth may occur when you have populations of bacteria or anything similar, which you may find in a laboratory. So in this lesson, we'll be looking at solving exponential equations. So we've got simple exponential equations, complex exponential equations, and using the CAS to solve exponential equations. Again, similar to the previous lesson, some of you may have seen this concept previously in your middle years mathematics or unit 1 and 2 mathematics. That's why there is no study design dot point for this particular lesson. So simple exponential equations. So exponential equations are the same base. So when solving exponential and logarithmic equations as well, we need to ensure that they are of the same base. So for example, with indices of a base of a to the power of x equals a to the power of y implies that x equals y. So we essentially, because they have the same base, we can work with the powers to solve any particular equation. And in this case, the base has to be a real number that isn't simply 1. The reason that this is true is given that when we take the log base a of a to the power of x, that equals x, and the log base of a to the power of y, that equals y, referring to our log laws. And thus we can see that taking a logarithm of both sides, we are left with x equals y. And we're going to go into this idea of the review of log laws later on in this unit, but it's a good way to think about the relationship between exponentials and logarithms really early when we're thinking back to solving simple exponential equations. So looking at these two worked examples, so we have 2 to the power of 3x minus 3 equals 8 to the power of 2x. So this particular question actually came from a 2014 VCEE exam 1. So again, it's a really common question you get to see on those end of year examinations. So let's first look at this particular part in part A. So we're 2 to the power of 3x minus 3 equals 8 to the power of 2 minus x. As mentioned previously, you want to have the same base. So you could technically make the 2 to the base of 8. However, it's always encouraged to go to the smallest possible base. So 2, you can't make 2 any smaller. However, you can make 8 smaller. And you know we have to get it to a base of 2 because the left-hand side is a base of 2. So how can we rewrite 8 to a base of 2? Well, as we've seen in the past, 2 to the power of 3 is equal to 8. So therefore, we can rewrite this equation as, once I get the correct color, 2 to the power of 3x minus 3 equals 2 to the power of 3 times 2 minus x. That's really important that you have the brackets there, because then we're going to have to multiply 3 by 2 minus x. So the left-hand side stays the same, so 2 to the power of 3x minus 3 equals 2 to the power of 3 times 2 is 6. 3 times negative x is negative 3x. And now we have everything as we need to have for in terms of the same base. So at this stage, we're just going to disregard that base of 2, so we're going to work with the powers. So we're going to have 3x minus 3 equals 6 minus 3x. Adding 3x to the left-hand side gives us 6x minus 3 equals 6. Adding 3 to the right-hand side gives us 6x equals 9. And finally, dividing both sides by 6, x will equal 3 over 2. And 3 over 2, because the common factor between 9 and 6 is 3. So 3 goes into 9 3 times, and 3 goes into 6 twice. So we're left with x equals 3 over 2. Now let's have a look at part B. It's a little bit different. We have 3 to the power of 2x minus 4 equals 1. Same process. We want it to the same base. So obviously we can't, the 3, can we get to a base of 1? Not necessarily. So we're going to look at how can we get 1 to a base of 3? Well, we know if we think about our zeroth as the 0th power, anything to the power of 0 equals 1. So we could rewrite 3 to the power of 1 as 3 to the power of 0. So we would have 3 to the power of 2x minus 4 equals 3 to the power of 0. And now we have that same base. So it's going to become 2x minus 4 equals 0. Add 4 to both sides, we get 2x equals 4. And finally, divide both sides by 2. We have x equals 2. So that's for part B. So just looking at that VCEE report in regards to part A, so some students attempted to use a common base of 8. So yes, as I mentioned, it is possible. You have to divide by the power of 3 rather than multiply. So if we think about how we went from a base of 8 to a base of 2, we multiplied the 2 minus x by 3. If you were to go on the left-hand side, if you were to go from 2 to 8, instead of multiplying by 3, you would have to divide by 3. So that would become 8 to the power of x minus 1, which again would work for you. However, it's not necessarily, a lot of students didn't necessarily do that correctly. So it's something to keep in mind. Personally, I always encourage students to go to the smallest possible base rather than go up to a base to make them common. But again, it's whatever you're more comfortable with, because they technically do both work. You just have to remember the order of operations in which you do them. So now looking at complex exponential equations. So we've looked at simple exponential equations in the sense of, we've had the same base or we've been able to easily get to the same base. Now we're going to be looking at complex exponential equations, and this may not be the case. And you may have to notice certain things, and in particular, hidden quadratics, a really common question that comes up in the exam that sort of wants to stretch students. And it's probably one of my favorite applications of quadratics outside of that actual topic, if you like, when you're in that middle years space, and it really comes up quite nicely or to me anyway, in when we're looking at exponential equations. So what are hidden quadratics? So basically they're common when we're solving these types of exponential equations, and why they're hidden is because you kind of have to look for them, and we have to use substitution to make them. So we're going to look at this particular example here as well. So we've got 2 to the power of 2x minus 4 times 2 to the x equals 12. So you may ask yourself, where's the quadratic here? We're going to get to the deep dive first. So when we're looking for hidden quadratics, we want to look for a polynomial in the power of each of the indices. Okay, so for example, if you have a to the power of 2x plus a to the x plus a, what we can see is we have a 2 at the front, we have that sort of squared at the front, if you like. Then we have plus a to the x, and then so you have x squared plus x plus plus c. And essentially what you have is ax squared plus bx plus c. You have that quadratic form, and you can see it's also in that sort of polynomial form. Even if you like to sort of make this a little bit clearer, this would be a to the power of x squared plus a to the power of x times 1 plus, and so on. So we can see we have something squared in our first term, then x in our second term, and then so on, in terms of how you normally see a quadratic. So let's look at this example, 2 to the power of 2x minus 4 times 2 to the power of x equals 12. So if I'm just going to rewrite this first term, similar to what I did with the a to the power of 2x on the right-hand side of the screen. So this is simply 2 to the power of x squared minus 4 times 2 to the x equals 12. So what we can notice, we have a term 2 to the x, and it's squared, and then it's not squared. So let's use a letter just to represent this 2 to the power of x. So let u equal 2 to the power of x. What we'll notice now is, well, if we're substituting u into the expression or the equation above, we would be left with u squared minus 4u equals 12. When we want to solve quadratics, we want to make sure the right-hand side is equal to 0. So we're going to have u squared minus 4u minus 12 is equal to 0. Now we can see this is in polynomial form. This is a quadratic. So we've moved from this exponential equation that we started with into a quadratic that we can now be able to solve. So if we look for two factors of negative 12 that add to give negative 4, so negative 6 and positive 2, so of u minus 6 and u plus 2 equals 0. Use our null factor law from quadratics that we know. U equals 6 or u equals negative 2. However, there is a trick for this. However, because you can't have a value when it's raised to a number equals a negative value. So for example, if you raise something to the power of 0, it equals 1. You can't get 2 to the power of 3 that would equal a negative value. It just doesn't happen. So in this instance, when we're solving for exponential equations, we need whatever we're solving for to be greater than 0. So essentially, we can disregard that solution for u equals negative 2 because u has to be greater than 0. U equals 6, but what did u equal? U equaled 2 to the power of x. So to solve this, you would have 2 to the power of x equals 6. And we can't simplify this because we don't have the same base. However, we could, to undo an exponential, use a logarithm of that same base of 2. So we're going to take x would equal log 2 of 6. So that's sort of, we'd set up in terms of getting from our exponential equation into a quadratic, solving the quadratic, and then putting it back into our exponent, or putting back the 2 to the power of x and solving for x using that logarithm. So it's sort of the first time that you may see a logarithm in this instance. However, we're going to go in more detail later on in future lessons as well. So the key thing with hidden quadratics is to try and look for that power when you, or try and rewriting it in quadratic form and then using substitution to help you solve that quadratic, and remembering that the solution has to be greater than 0. The reason being because when you take the log of a negative value, it's undefined, it doesn't exist. So it always has to be positive. So using this example, so 5 to the power of 2x minus 2 times 5 to the x minus 3 equals 0. So again, we're just solving for x, and again, it's an end-of-year examination question. Actually comes from Queensland, but again, it's very similar to what you'll see in the VCE end-of-year examination. So first thing I want to do is let you, or rewrite it if you like, before I even let you equal anything. Let's rewrite this to make it a little bit clearer for ourselves. So this is 5 to the power of x squared minus 2 times 5 to the power of x minus 3 equals 0. So now we can see, okay, let's let u equal something. You don't necessarily have to use u, you can use m, p, whatever you like. I prefer u in this instance. So just state what I'm letting u equal. Let u equal 5 to the power of x. And so therefore we have u squared minus 2u minus 3 equals 0. Two factors of negative 3 that add to give negative 2. We're going to have u minus 3 and u plus 1 equals 0. Therefore, u equals 3, or u equals negative 1. But as we know, u has to be greater than 0. Therefore, u equals 3 as u has to be greater than 0. So we're not quite done yet. Some students sort of stay there. However, we can't stay there because we haven't necessarily solved for x. Yes, we've solved for u, but what is u? We let u equal something, and in fact, we let u equal 5 to the x. So now we can state, well, 5 to the x equals 3. We want to take a logarithm, so therefore we're going to take the log base of 5 of both sides. So we're going to have x equals log base 5 of 3. And that's your final solution in exact value. So an exam 1 question, if you get a logarithm in this form, that's okay. It's an exact value. That's how you'd be expected to leave your answer. Okay, so that's sort of that's an example of that hidden quadratic. So solving exponential equations using the CAS. So in this section, we're going to visit ways to use the CAS to solve exponential equations. And this is particularly useful when we're unable to get to the same base, or when the hidden quadratic requires the quadratic formula and may be algebraically challenging to solve. So in the cases previously, yes, as complex and as challenging as the hidden quadratic questions are, sometimes we might not be able to solve the quadratic easily, and we may need the our CAS to solve this as well. So when we look at the example below, so solve the following for x, we have 5 to the power of x minus 8 on 5 to the x equals 2. So how would we go about solving this on our CAS? So if we're solving this equation, so we're going to put it in, well, first we're going to make a calculator, so add calculator. Then we're going to put in our equation, but before we do that, we want to solve. So we can go menu, algebra, solve. So we're going to solve 5 to the power of x minus 8 divided by 5 to the power of x. Oh, what's happened there? 5 to the power of x equals 2, comma 0, or comma x, I should say. Not w, missed it by that much. So just double checking, we have solve 5 to the power of x minus 8 on 5 to the x equals 2, comma x. Press enter, and we finally have x equals 2 log 2 on log 5. This will happen if your CAS is in exact. It could potentially happen if it's in approximate, if it's in order as well, so if it's in automatic. However, if you do want it to find it to X amount of decimal places, we would go Control Enter, and x would equal 0.86135, etc., 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 and you would round accordingly. So solving on the CAS, you'll simply have menu algebra solve, plug in your the equation that you've been provided, comma x, and then if you do get an exact value, make sure you do press Control Enter for the decimals. Putting this all together now, we're going to be looking at or finding the value of x again. So it's the value of x such that 2 to the power of 2x minus 16 to the power of x plus 12 is equal to 0. is true for when x is equal to which? So x would equal 1. So how do we go about this particular question? And again, we're going to go about it without a cas. So we've got 2 to the power of 2x minus 16 to the power of x plus 12. So again, in the past, we've sort of seen, there's a hidden quadratic somewhere. In this case, there is as well, but it's a little bit harder to see. And there's a bit of a trick in terms of the 16. So 16 can be rewritten using a base of 4, but we can also rewrite 16 using a base of 2. So 16 can be rewritten as 2 to the power of 4 to the power of x. So that would become 2 to the power of 4x. So if we rewrite this whole equation, we would have 2 to the power of 2x minus 2 to the power of 4x plus 12 equals 0. So let's rearrange this just to have the highest power. So in this case, the 4x would be higher than the 2x. So we would have negative 2 to the power of 4x plus 2 to the power of 2x plus 12 equals 0. So you may be thinking, where is this hidden quadratic? But what we mentioned before when we were looking at hidden quadratics is looking for the multiples of 2. So you'll see, well, we have 2 to the power of 2x. How can we get from 2 to the power of 2x to 2 to the power of 4x? Before we get to that, let's take out this negative just to make our life a little bit easier. So taking out the factor of negative 1. So we're going to have negative 2 to the power of 4x minus 2 to the power of 2x minus 12 equals 0. And so therefore we're left with 2 to the power of 4x minus 2 to the power of 2x minus 12 equals 0, because essentially we've divided by negative 1. So now we want to rewrite that 2 to the 4x using that base of 2 to the power of 2x. So that's going to become 2 to the power of 2x squared minus 2 to the power of 2x minus 12 equals 0. So you can see we've got that quadratic now. So let's let u equal 2 to the power of 2x. So we're going to have u squared minus u minus 12 equals 0. Two factors of negative 12 that add to give negative 1 are negative 4 and positive 3. So we're going to have u minus 4, u plus 3 equals 0. So therefore u equals 4 or u equals negative 3. But again, we can disregard that because u has to be greater than 0. So therefore u equals 4. Again, not finished yet. We have to substitute back in for what u was, and we let u equal 2 to the power of 2x. So we can say, well, therefore, 2 to the power of 2x equals 4. And you'll notice we could use a logarithm, but we can get to the same base. So 4 can be rewritten as 2 to the power of 2. So we can have 2 to the power of 2x equals 2 to the power of 2. Disregard the bases now, so we can have 2 to the power of x equals 2. Divide both sides by 2. And we're left with x equals 1. So in summary, when we want to solve exponential equations, where possible, simplify to the same base. Okay, so in these cases, we can then treat a to the power of x equals a to the power of y simply as x equals y and go on our merry way of solving those equations. Essentially, it almost becomes linear for the most part. Be aware of hidden quadratics is probably the second key thing that you have to look for. So it is a trick that is really common in exams. You're going to see an exponential equation most likely in exam 1 where you have to solve, and hidden quadratics is sort of that more challenging aspect of solving an exponential equation. So look for those common factors. In particular, look for those multiples of 2 in the powers. So whether you have 2 to the power of x and then to the power of x, so that's a multiple of 2, or you have to the power of 4x and to the power of 2x, again there's a multiple of 2. And you could potentially even have 2 to the power of, you can have to the power of 8x and to the power of 4x, again a multiple of 2. So it's something to look for as well. So be careful. But again, hopefully with all of these skills, you'll be able to answer a wide range of exponential equations by hand as well as using your CAS. In the next lesson, we're looking at applying not only our index laws, but also solving these exponential equations to help us sketch exponential functions. So welcome back, and in this session, we'll be looking at sketching exponential functions. But before we get into that, we have this article of the mining sector in Tanzania is experiencing exponential growth. So exponential growth comes up a lot in articles. We've seen it a lot over the past few years, and we'll continue to see it all the time because, again, it is something that sort of in articles is used quite a lot. But we want to see what it actually looks like mathematically. What is exponential growth? What is exponential decay? And that's something we're going to be looking at in this lesson. So sketching exponential functions. So we're going to be looking at what is the exponential function and features of these functions. So exponential functions, we're going to be looking at growth and decay. The general form of an exponential function can be given by f of x equals a to the power of x, where a is an element of R, where a is a real number. So growth, exponential functions grow when a is greater than 1, and exponential functions decay when a is between 0 and 1. So if we look at the two examples, we have f of x equals 2 to the power of x, we can see that's growth, where f of x equals a half to the power of x, that is representing decay. So again, we're sort of growing up to the right, growth, and then going down to the right for decay. You'll notice some students may think, why is it not negative? Because it's, if it's going down, it should be negative. However, it's about the fact that we're sort of halving. So every time that you halve, you're getting smaller, and that's decreasing, rather than if the a value is being negative, it's just a reflection. And again, you can still technically grow, and we'll see this later on. However, at the moment, decay, that factor will have to be between 0 and 1. So it's sort of how much are you losing, if you like, in terms of percentage. So in terms of a half, again, you're losing 50% every iteration. If you think of interest, let's think of depreciation. If we depreciated by 10%, again, the value of an asset is decreasing, so it's decay. So sketch the graph of f of x equals 3 to the x and g of x equals 5 to the x on the same set of axes. Label the point x equals 2 and the y-axis intercept for each of these functions. So what we can see that's common between these two functions is we have growth. Okay, the reason why we can see we have growth is because we have 3 to the x, so 3 is obviously bigger than 1, and 5 to the x is also 5 is bigger than 1. So the general shape of these graphs will be fairly similar, but what does the impact of the 3 and 5 have to do on these particular graphs? So I'm just going to label a point x equals 2 on our graph to start off with. So let's say x is equal to 2 here. Okay, so that would be 1, and so on, 3, etc. And we want the y-axis intercept. So y-axis intercept, like any graph, we let x equal 0. So for the y-intercept of f, we're substituting 0, so it's going to become 3 to the power of 0. Using that 0th power, 3 to the power of 0 is simply just 1. Okay, so we have 0, 1. And for g of x, again, substituting in 0, you have 5 to the power of 0, which also equals 1. So again, they're both going to go through that point. However, let's have a look at x equals 2 to see how they behave at that point. So if we substitute 2 into f of x, we're going to get 3 squared, which will equal 9. And g of 2 is going to be 5 squared, which equals 25. So my scale is going to be quite off, but that's okay. So let's say that's going to be 2, 9. So double that's about there. So 25 would be roughly up here. That's going to become 225. So let's try our best to sketch this graph. It's a bit of a wonky graph, but nonetheless, we can see it's sort of growing. It's growing. And then we're going to approach that axis because there's an asymptote, which we're going to get to in a moment. And 5 to the x, so it goes through the point 225. So So it's going to be becoming a lot steeper. So you can see we're growing at a lot faster rate in g of x as compared to f of x. So even though they technically both have the same y-intercept and they would have the same asymptote, they actually grow differently. So that although it's growing, that factor does affect sort of the steepness of your graph, if you like. So for exponential functions, there is a horizontal asymptote at y equals k. So this means that the vertical translations for exponential functions are really important because they tell you where this asymptote is. So reflections, dilations, and translations, we're going to first start with reflection. So reflection in the y-axis, if we had the equation. So looking at a reflection in the y-axis, let's start with the original graph of y equals a to the x. And again, I apologize for that wonky graph. So what would a reflection in the y-axis look like? I'm going to do this with a different color. Let's go with a green. So we would have, and again, going through that same asymptote, same shape, purely just a reflection. And this would be y equals a to the power of negative x. So again, there's a negative at the front of that x. Looking at a reflection now in the x-axis. So again, let's first draw our initial graph of y equals a to the x. Let's go with blue. So reflection in the x-axis means it's sort of there's a mirror on that x-axis and it's being reflected about that. And again, the shape stays the same. However, now it's being mirrored about the x-axis. So we're going to have y equals negative a to the power of x. So reflections are quite important because again, they tell you sort of the general shape and whether or not you're going to have intercepts and whereabouts you're sort of what the shape of your graph is. I just want to touch on reflections in the y-axis. So some people may be getting confused with sort of decay and why does that resemble a decaying graph. Let's think about this for a moment. So let's think about, so let's say we had, so y equals a to the power of negative x. That's equivalent to 1 over a to the power of x. So in that instance, if we think about what a may be, let's say it was 2. So let a equal 2 in this particular scenario, you would have 1 over 2 to the power of x. So basically, as x gets bigger, you're raising 2 to a bigger number. So it's almost, so let's say if you had a half to the power of 1, it's, a half. If you had 1 over 2 squared, it's a quarter. 1 over 2 cubed, it's an eighth. So it's getting smaller. So y equals a to the power of negative x also resembles the graph of a decaying function. Okay, so they do look the same as if you had a half to the power of x or if you had 2 to the power of negative x. Okay, so it's another way of thinking about decay. And in this instance, really what it is a reflection in the y-axis. Okay, so now let's look at dilation. So starting with the dilations from the x-axis. So if you have y equals a to the x, that's a little bit better. So this is going to be y equals k times a to the power of x. So that k is going to be essentially multiplying and pulling it away from the x-axis. So it's affecting the y values. Now let's look at a dilation from the y-axis. So it's essentially pulling away from the y-axis or closer to. So again, let's look at y equals a to the x. These obviously where a is growing. So then this would be y equals a to the power of b x. So essentially what we're doing, so from the y-axis, if that b value gets bigger, we're stretching it away from the y-axis. So what's happening is from the x, you're pulling it away from the axis or pulling it towards. And from the y-axis, you're pulling it away or towards from the y, and it's going to be affecting your x values, whereas from the x-axis will be affecting your y values. So sort of it's the opposite. And it's another way of thinking about the transformations of these particular graphs. So translations in the y-axis, as I mentioned before, they're again really important because they tell us where the horizontal asymptote may be. So let's look at just an equation, y equals a to the x. And this could be, let's go with the red. This could be y equals a to the x minus k. So essentially we've shifted it down by k units. So that means we're going to have an asymptote at y equals negative k. Same thing would happen if we shifted it vertically, or in the vertical direction, the positive vertical direction, I should say. So if we had y equals a to the x plus k, again, you'll just shift it up, and the asymptote would be at y equals k. So again, if you shift it down, it's just negative k. If you shift it up, it's just positive k is where your asymptote will be. Really important, again, you do not touch your asymptote because technically the function doesn't exist at that particular point. Translation in the x-axis. So again, this would be something where you have our original function. So y equals a to the x. Probably should have drawn it first, but that's okay. There we go. And then let's say we had y equals a to the x minus h. So sort of shifted it across by h units. So again, the intercept will be slightly different because we have, again, substituting x equals 0, you would have a to the power of negative h, whatever, again, a and h are. However, it has been a shift in the positive direction of the x-axis in this particular situation. If you had a to the power of x plus h, you would have a shift in the negative direction of the x-axis. So the general shape when you're translating the x-axis for exponentials doesn't change too much. It will change where your intercept lies, but the shape will stay relatively the same, and you won't see too much of a difference. However, when you're translating the vertical axis, and because it's so important for the asymptote, that's going to have a big impact on what your graph looks like for exponential functions. So this worked example, we're going to be sketching the graph of f of x equals 2 to the power of x minus 4 over the domain x is an element of negative 5 to 5. Label all relevant features and endpoints. So in this particular scenario, when we have an exponential function, we want to, all the relevant features are obviously our intercepts, our x and y intercepts, if for whatever's relevant, and finally our horizontal asymptote as well, and in this case endpoints, because we're being given a specified domain. So we'll get to the endpoints last, but let's first look at the function 2 to the power of x minus 4. What we can notice is we have a horizontal asymptote at negative 4. So we're going to go with, first let me just label the axes, f of x and x. So we're going to have negative 4. So this is going to be f of x equals negative 4. And we have 2 to the power of x. So generally speaking, what we can see is we're growing. So we're going to have something that looks like it's going in that direction. So that means we're going to have an x and a y intercept. However, we don't know where they are. So this current graph could be accurate. However, high chance is that it's not. So I only did it to know that we're going to have an x and a y-intercept and to solve for both. So let's first look at our y-intercept. So y-intercept, we're going to let x equals 0. So substituting in 0, so f of 0 is equal to 2 to the power of 0 minus 4. 2 to the power of 0 is 1, minus 4 is negative 3. So there's our y-intercept at 0, negative 3. And that means now that our x-axis intercept has to be positive because, again, it's growing. So if you got a negative value, you will know you're incorrect. So it's sort of another way of knowing exactly where your intercepts are will help you double check any algebraic working that you're not sure of. X-intercept, let f equals 0. So we're going to have 2 to the power of x minus 4 equals 0. 2 to the power of x equals 4. We have an exponential equation. We can solve this. We need to get to the same base. 4 can be rewritten as 2 squared. So we're going to have 2 to the power of x equals 2 squared. Finally, x equals 2. So x equals 2, that's 3 there. So that would have to be roughly 2. So 2, 0. And then we also now have our endpoints to worry about as well. So substituting in negative 5 and 5. So let's go up here. So endpoints. Probably should have done my intercepts on the left-hand side of the screen. That's okay. So we're going to have f of negative 5 is equal to 2 to the power of negative 5 minus 4. 2 to the power of negative 5 we can rewrite using positive indices, so that's going to be 1 over 2 to the power of 5 minus 4. 2 to the power of 5, we've got 2 squared is 4, 8, 16, 32, so 1 over 32 minus 4. When we add or subtract fractions, we need the same denominator, so we need to get that 4 to be over 32 as well, so we're going to have to multiply 4 by 32. 4 times 32 is 128, so it's going to be 1 over 32 minus 128 over 32, and that becomes negative 127 over 32. So now that's going to be approximately 3.9 or something, negative 3.9 or something close by, because it's 1 over 32 minus 4. So you can see we're approaching that asymptote. It obviously can't be below negative 4 because then it doesn't exist at that point. So if that's 2, that would be 3, 4, 5. So let's say it's somewhere here. And let's label that point. That's negative 5, 127 on 32. Negative. There we go. There's that point. And we're going to find our upper bound of the endpoint. So f of 5 equals 2 to the power of 5 minus 4. 2 to the power of 5 is 32. So 32 minus 4 gives us 28. That was a little bit easier to solve. So 28, if that's 4, it's probably going to be really, really high. So it's 2, 5. Let's go up here. So it's going to be 5, 28. My scale was a little bit off, but that's okay. So now connecting all our points. We can see where I put an arrowhead accidentally, but nonetheless, that's the graph of f of x over that specified domain. So when you're sort of going about sketching these graphs, you want to see one where that horizontal asymptote is, see the sort of the general shape of your graph, whether it's growing, decaying, and then looking for your key features. So your two intercepts, sometimes you won't have two, so that's why it's always good to check. And then obviously if you have endpoints, to find those particular endpoints. So the function h of x equals negative 2 to the power of x minus 2 plus 4 has a domain and range respectively of. So the function h of x has a domain of x as an element of R. That means it's all real numbers. And a range from negative infinity to 4. So if we look at this graph, we can see it's being shifted vertically up by 4 units, meaning that our horizontal asymptote is at y equals 4. So let's draw that in. Okay, so what we can see as well, so yes, we've got 2 to the power of x minus 2 represents growth. However, it's being reflected in the x-axis. So therefore, our graph is going to look something like so. It's obviously not exactly that, but it's something similar. So what we can see is that for the x values, well, the x values go from negative infinity to positive infinity, and the y values go from negative infinity all the way up to 4. They approach 4, they don't actually get to 4. So that's why you always have to have a curved bracket for when you have an asymptote. So therefore, it can't be negative 4 to infinity, because it's not as if it's been shifted down by 4 units and it's growing. It's actually being reflected, so it's going to be from negative infinity to 4, leaving us with the answer of C. So in summary, when we have the exponential functions are given with the form f of x equals a times b to the power of x minus h plus k, where a is the dilation factor in the y-axis, h is your translation in the x, k is your translation in the y. And k is particularly important because that tells you where the horizontal asymptote is. So what do you need when you're sketching exponential functions? Well, you need to know the equation of the horizontal asymptote, and you have to make sure that you label that. You need the actual axial intercepts, so the x and y intercepts. And finally, consider any relevant transformations, because when you consider these transformations, it helps you sort of visualize where your graph is and what intercepts you need and sort of what values they will have before you even start to solve. Okay, so again, that's sort of my tip as well. Know your transformations, as at times, particularly if you shift vertically and there's no reflection, you actually won't have an x-intercept, and you may get confused when you can't solve for one as well. So that's why knowing your transformations is really important. So next lesson, we move into the sort of second part of this topic, if you like, and that is logarithms, and we're going to be doing a review of log laws. So the origin of logarithms. So John Napier published his work on logarithms in 1614 as a tool to calculate large numbers. So these were particularly important for calculating or computations found in astronomy and navigation. So a little bit of a fun fact of, where did logarithms come from? And again, you can look up his story to find out a little bit more information, as well as we sort of embark on our work on logarithms for this part of the topic. So in this lesson, we'll be looking at a review of log laws. So again, there's no study design dot point for this lesson, given that these log laws you may have come across in middle years mathematics as well as unit 1 and 2. So looking at a proof for the property of adding logarithms, let's start with log a of m equal to x and log a of n equal to y. So from this we can see that by undoing the logarithm of both in each case, we're going to have m equals a to the power of x and n is equal to a to the power of y. So if we found m times n, this is going to be equivalent to a to the power of x times a to the power of y, which is equal to a to the power of x plus y. So if we took the log of both sides, we would have log a of m times n is equal to log a of a to the power of x plus y. And when log base of a, in the argument it's a to the power, log a of a becomes 1, so we're going to be left with log a of m times n is equal to x plus y. And we can recall from the start we said x was equal to log a of m and y is equal to log a of n. So therefore we can conclude that log a of m times n is equal to log a of m plus log a of n. So there's our proof of that particular property. So what it sort of came about was, well, we let log a of m equal x, log a of n equal y. We rearranged, so we undid the log by raising both sides to the power of a. So that allows you with the m equals a to the power of x and n equals a to the power of y. Multiplying together, because we know in index laws, when you multiply two indices of the same base, their powers add. We took log a of both sides, which is perfectly fine because we did it to, again, the left hand and the right hand side. So log a of m times n is equal to log a of a to the power of x plus y. That means we just have x plus y because log a of a becomes 1. So log a of m times n is equal to log a of m plus log a of n, and therefore proving that particular property. Now looking at subtracting logarithms, so it's log a of x equals log a of y equals log a of x divided by y. So again, we can go about the proof very similar to what we've done previously. So again, we can say, using our definitions in the previous section, we can say that log a of m is equal to x and log a of n is equal to y. So therefore, again, we have m is equal to a to the power of x and n is equal to a to the power of y. Dividing m, or m divided by n, this is equivalent to a to the power of x divided by a to the power of y. So knowing in this instance that we have indices of the same base, we subtract their powers. So m divided by n is equal to a to the power of x minus y. Let's take the log of both sides. So log base a of both sides, so we have log base m divided by n is equal to log base a of a to the power of x minus y. Again, log base a of a becomes 1, so we're left with just x minus y. So we have log a of m divided by n is equal to log, oh no, we've gotten rid of the log because log a of a was 1, so it's just x minus y. And then when we substitute back in for what we initially let x and y equal, we're going to have log a of m divided by n is equal to log a of m minus log a of n. So again, proving that when we're subtracting two logarithms, it's the equivalent to dividing the argument of the first and the second. So log a of x minus log a of y equals log a of x divided by y. Logarithms of powers. So we're going to be looking at logarithms of positive and negative powers. So in the case of, okay, so looking at the logarithms of powers, so we're going to be looking at positive and negative powers. So when we have a positive power, so log a of m to the power of p, this simply equals p log a of m. I call it the plug law. Another way of sort of remembering to bring that p to the front, if you like. And now we're going to be looking at a proof of this rule or this property. So we're going to let m equal a to the x, given that we're working with a base of a. So that's why we've chosen to have m written as a base of a to the power of x. Now substitute this in for m, so we're going to have log base a of a to the x to the power of p. Using our index laws to combine that, so that it becomes log a of a to the power of xp. We know that a to the power, or log a of a just becomes 1, so this becomes x times p. And if we refer back to what we let m equals a to the power of x. So let's just go back to that for a moment. So let's rearrange for x. So x is going to be equal to log base a of m. Substitute that into x times p. We're going to have, therefore we're going to have x times p is equal to log a of m times p, which is equivalent to p log a of m. So again, proving that all we're really doing is moving that p to the front. So it becomes a p log a of m. This is just, again, proving that particular property. So the plug law, I like to call it, you're bringing the p to the front, or bringing whatever power that is to the front, and hopefully simplifying it as you can. Now looking at logarithms of negative power, so we've got log a of m to the power of negative 1. That equals log a of 1 over m, which equals negative log a of m as well. So in this particular instance, again, if you think about where does the m to the negative 1 come from, think back to the index law proof. We have, or m to the power of 0 divided by m. That leads you to log a of 1 over m. Or again, you can use the plug law that we just looked at, and where you bring that negative 1 to the front. Okay, so it's negative 1 log a of m, or in other words, just negative log a of m. So a tip, using powers when working with logarithms is really, really important. The purpose is to allow us to rewrite either really small or rather large numbers. So again, we're going to be working with them when we add and subtract, as well as when we're working with powers. So some other useful log laws, we have law 5 and law 6. Log a of 1 is equal to 0, and log a of a is equal to 1. So log a of 1 equals to 0. If we think about that, to undo a log, we raise both sides to the power to a base of a. So again, undoing a to the log a becomes 1, so it's just going to become 1. We're left with our argument. 1 equals a to the power of 0. And we know that's true because we know using the 0th power that anything to the power of 0 is equal to 1. Finally, law 6, again, undoing that log of base a, we raise both sides to the base of a. So we have a equals a to the power of 1. Again, we can see that is true as well. So looking at our deep dive, logarithms of negative numbers or 0 are undefined. And that is it leads to a non-real result, given that when you raise a base to the power of a real number, you will never get 0 or a negative real number. So you can never raise, let's say for example, you had 2 to the power of negative 4. 2 to the power of negative 4 is equivalent to 1 over 2 to the power of 4. So it's 1 over 16. You're never actually going to get 0. You're never actually going to get a negative value. Okay, so that's why we're always looking for values where it's greater than 0. So simplify the following. We've got log 2 of 6 plus log 2 of 5. So again, we're adding logarithms, meaning we're multiplying the arguments, the inside parts of the logarithms, as people like to remember that as. So log 2 of 6 plus log 2 of 5, this is going to become log 2 of 6 times 5, which is equal to log 2 of 30. I always like students to think about, can we simplify that 30 to a base of 2 in any way? In this case, we cannot, so we simply leave our answer as log 230. Now let's look at B. So we've got log 3 of 10 minus log 3 of 5. We're subtracting logarithms, meaning we're dividing the arguments. So we're going to have log 3 of 10 divided by 5. 10 divided by 5, it gives us 2. So we're left with log 3 of 2. So another part of that same word example, again, we're starting to use potentially a combination of laws in some instances. So simplify the following. We got log 4 of 64. So I want you to think about, is there any way we can simplify that 64 to a base of 4? So 64, 4 times 4 is 16, times 4 is 64. So we can rewrite that as 4 cubed. So this becomes log 4 of 4 cubed. And now you might notice we can actually use our plug law. We can bring that 3, we can bring that to the front. So this would become 3 log 4 of 4. And what you may also notice is we have log 4 of 4. The argument, what's inside the brackets, is equal to the base. When that happens, that becomes 1. So that's going to be equivalent to 3 times 1. And finally, we're left with the answer of 3. So log 4 of 64 simplifies to 3, or is equivalent to 3. Evaluate that, becomes 3. Now let's look at log 3 of 1 over 27. So in this instance, the 1 over 27, I know we've got a fraction, so it has to probably be something to do with a negative power. So 1 over 27, think about that base of 3 for a moment. 27, that can be rewritten as 3 to the power of 3. So we're going to have log 3 of 1 over 3 cubed. Can't really do much in that form. However, we can rewrite this using a negative index. So we can put 3 to the power of negative 3 as our numerator. So this would become log 3 of 3 to the power of negative 3. Again, you'll see we can use our plug law, bring that negative 3 to the front. So it's negative 3 log 3 of 3, lots of 3's. So log 3 of 3, when the argument, what's inside the brackets, is equivalent to the base, that becomes 1. So we're left with negative 3 times 1. And finally, our solution being negative 3. So in summary, we have adding and subtracting logs. So adding logs, we multiply x and y. Subtracting, we divide. Logs with positive powers, again, bringing p to the front. A negative power becomes the same law, which make it negative. Log a of 1 is equal to 0. So whenever your argument is 1, it's equal to 0. And logs where the argument and the base is the same, they equal 1. So when you're simplifying logarithms, the key is that you only simplify logarithms that are of the same base unless they become integer values. Okay. In our next lesson, we're going to be looking at solving logarithmic equations using a combination of these laws that we've learnt in this lesson. And so working with natural logarithms. So we're not necessarily in a forest. We're going to be working with log base of e and log base of 10 and generally logarithms of the same base. However, we're going to be looking to see how we can solve for x using logs and hence solving logarithmic equations. So in this lesson, we are looking at solving logarithmic equations, and we're looking at solving them with and without the use of a CAS. Again, there is no study design dot point for this particular lesson, as most of it is covered in middle years and Unit 1 and 2 mathematical methods. So solving logarithmic equations. To solve these equations where the value of the unknown is in the argument, so that is inside the brackets, we need to convert from log to exponential form. So for example, in this instance, we have log a of x equals b, so show that x equals a to the power of b. To undo a logarithm, we raise both sides or use the base of that logarithm to make it the base of both sides, essentially. So what would happen here would be we would have a to the log a of x equals a to the power of b. Whenever you have an index raised to a log of that same base, that becomes 1. Okay, so a to the log a becomes 1. You're left with purely what's inside the argument. So we're just left with x. So therefore, you have x equals a to the power of b. So we can get it into that exponential form. So that's converting from log form to exponential form. When we have multiple logs of the same base, we either want to add or subtract. We want to simplify first before we go into converting to exponential form. So looking at this example, solve log 4 of x plus log 4 of 8 equals 2. The first thing we want to do when we're adding logs is we want to multiply. So we're going to have log 4 of x times 8 just becomes 8x equals 2. Again, we're going to use a base of 4 to both sides. So we're going to have, just to keep it really consistent. You don't have to show this step of the working out later on. However, it's good just to see what we're actually doing to both sides. That's 4 to the 2. So this becomes 8x equals 4 squared, which is 16. Divide both sides by 8. And we're left with x equals 2. So again, you just simplify your logarithms and then convert exactly how we did in that first example. So in times where we don't have logarithmic equations with the same base, and that is we have them with different bases, we may need to be able to change their base. So for example, if we had log a of x and we wanted to change that to a base of log b, just because it may be easier for us to evaluate in the longer term, we need to be able to use a change of base formula. So let's, for example, look at the following. So let's say we had we've got y equals log a of x. Okay, so let's say we had, implying that a to the y equals x. So let's take log b of both sides. So let's start with a to the y equals x. So we're coming up from here. Take log b of both sides. You can do that because, again, you're doing it to both sides, so that's okay. So it's equivalent on each side of the equation. So log b of a to the y equals log b of x. Now we can use the plug law for that y, so it comes to the front. So we're going to have y times log b of a equals log b of x. That doesn't change. We can't simplify that any further. And then from this part, we can divide both sides by log b of a. So we're going to have y equals log b of x divided by log b of. And if we think about what y was initially, we can then state that log a of x is equal to log b of x divided by log b of a. So that's the change of base formula. So now we have the example, evaluate log 2 of 7 without a calculator. So we have log 2 of 7, and we want to use we essentially want to change that base. So I'm going to use a log base of 10. So what we can see, if this is essentially our a, and that's our x, we can look at and b would be 10 in this instance where I'm using a base of 10. So we can take log base 2 of 7 is equal to log base 10 of 7 divided by log base 10 of 2. So that's another way of rewriting log 2 of 7 without a calculator. So solve the equation log e of 3x plus 5 plus log e of 2 equals 2 for x. So this was a 2007 VCAR question from exam 1. So again, it's an exam style question. Is it from a fair while ago? However, it's something again that you're likely to see on that end of year exam in exam 1, where you weren't allowed to use a CAS. So as we mentioned before, when you're solving logarithmic equations, you want to simplify as much as you can first before converting to an exponential form. In this instance, when we're adding logarithms, we want to multiply the inside. So it's going to become log e of 3x, or 2 times 3x plus 5 equals 2. And then now let's expand those brackets. So it's going to become log e of 6x plus 10 equals 2. Now we can't simplify that any further from a logarithmic perspective. So we can convert now to exponential form or index form. So we can use a base of e to the other side. So it becomes 6x plus 10 equals e squared, and then we're going to have 6x equals e squared minus 10, so we're just solving for x. Divide both sides by 6, so therefore x equals e to the 2 on 6 minus 10 on 6. We can simplify that further, so it's e squared on 6 minus 5 over 3. So 5 over 3, because the common factor between 10 and 6 is 2. 2 goes into 10 5 times. 2 goes into 6 3 times. So we can say x equals e squared on 6 minus 5 over 3. Or you could probably leave your answer as x equals e squared minus 10 on 6 as well. So just from the VCAR report, so again, the question was generally answered well by students. However, students that incorrectly answered this question added 5 and 2 rather than applying the log law. So they accidentally did log e of 3x plus 7 rather than 6x plus 10, so actually multiplying. So they just added the 2 instead of multiplying the 3x plus 5 by the 2. So again, something to consider when you're adding two logarithms of the same base. You want to make sure that you're multiplying their two arguments together. So logarithmic equations with the CAS. So when we're solving logarithmic equations using our CAS, it's again very similar to when you're solving any other sort of algebraic equation. We're going to, so again, you would have menu, algebra, solve, and so forth. So in this example, we have used the CAS to solve log 2 of x minus 4 plus log 4 of x equals 2. So again, we're going to go to menu, algebra, solve, log 2, so control, where's log? Log is just above the 10 to the power of x. So I don't want 10 to the power of x, I want to go above it. So you're going to press control, log, and that's log base of 2, x minus 4, plus log 4, log base of 4 I should say, of x is equal to 2 comma x. Tell the CAS what we're solving for and press enter. Comes up with a really big surd. Let's press control enter again to give us a value, and we get x equals 5.67857, etc. To 2 decimal places, this would just be x equals 5.68. So again, if it comes up with a surd or a power that sort of you're not really sure of how to write it out, or it will take you probably a very long time to write out, just press control enter to get the decimal value or the approximate value. Solve the equation log 4 of x plus log 2 of x equals 3 for x. So this particular question was rather challenging because you had different bases. So you may have had to use a change of base formula. That's how we're going to go about it in the explanation. So if we have log, let's convert both of these. So log 10 of x divided by log 10 of 4. So that's just converting log 4 of x to a log base of 10. Now plus log 10 of x on log 10 of 2 is equal to 3. So now we can see we have log 10 of x plus log 10 of 2 squared. So we can use our plug law eventually. plus log 10 of x. We can't do anything to the right-hand side at this stage. Log 10 of 2 equals 3. So now we have log 10 of x, just such a process more than anything else, divided by log 2 log 10 of 2 plus log 10 of x on log 10 of 2 equals 3. So from this point on, what we can see, we've got fractions. We want to have the same denominator. It's close. It's 2 log 10 of 2 and log 10 of 2. So the right-hand fraction, we're going to multiply both the numerator and the denominator by 2. So this is going to become log 10 of x on 2 log 10 of 2 plus 2 log 10 of x on 2 log 10 of 2 equals 3. So let's come over here. So what you'll notice now is because we have the same denominator, we can actually multiply by 2 log 10 of 2 to the other side. So this becomes log 10 of x plus 2 log 10 of x equals 3 times 2 log 10 of 2. Now we can see we're going to have, let's get this. Okay. So now with the 3 times 2, let's not worry about the left-hand side for the moment. Let's focus on the right-hand side. So now let's try and simplify as much as we can. So we're going to have log 10 of x plus, I'm going to just bring that 2 back to x squared for the moment. So it's going to become log 10 of x squared equals 3 times 2 is 6. So it's going to become 6 log 10 of 2. Log 10 of x plus log 10 of x squared would become log 10 of x times x squared gives you x cubed, which equals 6 times log 10 of 2. So that 6 we can also put back to the power using that base of 2. So that can be written as log 10 of 2 to the 6. And because we have log 10 on both sides now, if we use the base of 10 on both sides, we'll notice that becomes 1. So again, we can sort of get rid of or disregard the log 10. And we're left with the argument. So x cubed equals 2 to the power of 6. And now we want to take the cubed root of 2 to the power of 6. So it becomes x equals the cubed root of 2 to the power of 6. That's equivalent to 2 to the power of 6 on 3, which is 6 divided by 3 gives you 2. So 2 squared, which is equal to 4. So x equals 4, and that's given in B. So that question there, quite a long process. And again, using that change of base the whole way through. So again, it's rare that you'll get something that complex, but if it does come up, you will know how to go about answering a question like that, where you have different bases and you're required to do it by hand. So in summary, when we're solving logarithmic equations, we want to convert to exponential form from logarithmic form. We want to simplify logarithms using log laws. And finally, we want to recall that the argument of a logarithm has to be positive. Again, that's one of the most important parts for when solving logarithmic and even exponential equations. The other thing that's also useful is change of base. So you have log a of x equals log b of x on log b of a. And for the most part, that log base b will generally be log base 10 as well. So in our next lesson, we're looking at sketching logarithmic functions. So again, we're putting everything that we've learned to a graph and seeing all their transformations and all their features as well. So I'll see you then. What is the common difference between bacteria and logarithms? So although that they are different, there is a common difference. That is, they are both the inverse of one another. For instance, an exponential graph, bacteria grows exponentially, whereas logs grow logarithmically, not literally. However, just for this particular scenario, we can see that they are the inverse of one another. And we're actually going to come to this concept later in this topic. So in this lesson, we're going to be looking at sketching logarithmic functions. In particular, we're going to be looking at features of logarithmic functions, transformations of logarithmic functions, and the domain and range of these functions. So features of logarithmic functions. So we're given by the formula f of x equals a log e, we're just using a base of e in this case, x minus h plus k. So a is our dilation factor in the y-axis, h is the translation in the x-axis, k is the translation in the y-axis. So h is basically moving our graph left and right. K is moving our graph up or down. So whether it's in the positive direction of the y-axis if k is positive, or in the negative direction of the y-axis if k is negative. So importantly, we have to remember for logarithmic functions that there is a vertical asymptote at x equals h, or where the argument of the logarithm is equal to 0. So again, you can basically solve that inequality of the argument for it to be equal to 0 or greater than 0. If we remember what the argument was, the argument of a logarithm is the expression of which the logarithm is operated on. So for example, if we had log 10 of x plus 1, the argument is x plus 1. Or if it's easy to remember, it's just whatever is inside the brackets of a logarithm. So firstly, we're going to be looking at dilation and reflection. So looking at dilations from the x-axis. So that means getting sort of pushed up. Okay, so dilation in or from, in this case, from the y. For dilations from the x-axis, so that means we're stretching it away from the x-axis. So let's look at just our standard graph to start off with. Let's call this y equals log 10 of x. So it's a base of 10. And that point there is going to be 1, 0. So if it was to draw something like y equals 2 log 10 of x, what would happen here? So it still goes through the point 1, 0, because again, let's just prove that it goes through this point. So to find our x-intercept, we let y equals 0. So we have 0 equals 2 log 10 of x. Divide both sides by 2. So we get 0 equals log 10 of x. Raise both sides to the power of 10. So 10 to the power of 0 is 1. So 1 equals x. So we can see that it goes through that point and it'll become steeper. So again, they do intersect at the point 1, 0. If we were to look at something like y equals a half log x, we can sort of assume what would happen. In this case, instead of becoming steeper, it will become less steep than the original graph of log 10x. So in this case, again, it would intersect at 1, 0. However, it is closer to the x-axis. So when we're looking at dilation from the x-axis, it's essentially how far we're stretching it away from that x-axis. And in this case, we can see that the furthest away is the green graph because that's been dilated by a factor of 2. Okay, whereas the closest one is the blue graph because that's y equals a half log 10 of x. Okay, so looking at dilations from the y-axis, so a little bit different from the x-axis because now we're essentially stretching it away from the y-axis rather than away from the x. So again, let's draw our original graph of y equals log 10x. We have an intercept at 1, 0. Now let's look at something y equals log 10 of 2x. So in this case, the y equals log 10 of 2x. That's actually a dilation of a half, so it means we're becoming closer to the y-axis. So in this instance, we're not necessarily going to have the same intercept. And the reason for that is because the number is inside of the argument, so that 2 is inside our argument rather than when we have a dilation from the x-axis, that 2 was outside. So if we look at our x-intercept, we can see we're going to have 0 equals log 10 of 2x. Taking 10 to the power of both sides, 10 to the power of 0 is 1. So we have 1 equals 2x. And finally, x equals a half. So we've actually shifted this graph closer to the y-axis. We're going to go through that graph. And these won't intersect. It's purely just been brought closer to the y-axis. So if we had y equals log 10 of a half of x. In this instance, because whenever you're dilating from the y-axis, it's essentially by a factor of 1 on n, whatever that n is the coefficient of x. So in this case, n is a half, so 1 divided by a half is 2. So that means that we're going to actually be shifting it away from the y-axis. And our x-intercept would actually be equal to 2 as well. That's going to be 2, 0. And finally, let's sketch our logarithmic graph. So all in all, dilations from the x-axis essentially shift away from the x-axis, and it's going to be at the front of the logarithm, whereas dilations from the y-axis will be inside of the argument. And it's always sort of remembering that it's by 1 on n, where n is the coefficient of that x value. Reflections in the x and y-axis. So we'll start with reflections in the x-axis. So again, let's start with our original graph of y equals log 10x, and intercept at 1, 0. Let's always label our graphs. Log 10 of x. So there's our logarithmic graph. So reflecting in the x-axis means it's going to affect our y value. Now y equals negative log 10 of x. So in this case, all our values now become negative. So it's essentially just flipping it about that x-axis. So again, it'll still go through that intercept of 1, 0. However, it starts from that top and then goes to the bottom right. So again, it's just essentially if there's a mirror on that x-axis, and the negative will be at the front of your logarithm. And finally, a reflection in the y-axis. So this reflection in the y-axis will now affect your x values. Function, where we go, y equals log 10 of x, y equals log 10 of negative x. So in this instance, instead of having an x-intercept at 1, 0, we're going to have an x-intercept at negative 1, 0, and it's going to go up towards the top left. So again, as if there's a mirror along that y-axis, we're flipping it about that y-axis. And so essentially what you can see is it's affecting our x values. So a reflection in the x, the negative is out the front. A reflection in the y-axis, the negative is inside the argument. Okay, translation. So looking at translations in the x and y-axis. So again, in the x-axis, it's our shift horizontally, and our translation to the y-axis is our shift vertically. Again, our original graph, so I'll draw them all, log 10 of x. So always have the 1, 0. So firstly, we're going to be looking at a translation in the x-axis in the positive direction. So to have it in the positive direction, we would have something like so. So we'd have y equals log 10 of x minus 1. So in this instance, this x minus 1 means we've shifted our graph right by 1 unit. So now our intercept would be at 2, 0, and our graph would look something like so. The difference in this case is because we've shifted it to the right, and it will be the same thing when we shift it to the left, we now have to worry about our asymptote. So there's a vertical asymptote whenever we shift our logarithmic graph left or right. So in this case, because we've shifted it right by 1 unit, normally there's an asymptote at x equals 0, but because we've shifted it right by 1 unit, there'll be a vertical asymptote at x equals 1. So to draw that in, you just draw it again a dotted line, and you will see that our blue line actually gets quite close to that asymptote, just to make sure that it never touches. So in this case, there's a vertical asymptote at x equals 1, and we've shifted that across by 1 unit because our intercept is at 2, 0. Now looking at translation in the negative direction. So let's assume we had y equals log 10 of x plus 2. So in this case, we can see that we've shifted our graph 2 units in the negative direction. And we're going to have a vertical asymptote at x equals negative 2. So if you like, you can put that in first. So it's a little bit off scale, but let's say that's x equals negative 2. Considering that we've shifted our graph by 2 units to the left, we can also do the same thing to the intercept. So we can move that 1, 0 to the left by 2 units. So moving it to the left by 2 units would then result in an x-axis intercept of negative 1, 0. So it's a little bit off scale compared to the others, but that's okay. And finally, we have something like so. So when we're translating our graph in the x-axis, it doesn't really matter too much about the shape. It won't affect the shape as much. What's more important is the position of the vertical asymptote. So again, when you're labeling your key features of the graph, the translation will tell you where your vertical asymptote is. Translations in the y-axis, in this instance, it's not going to affect where your vertical asymptote is. What it will affect is where your x-axis intercept will be. So let's say we have something like y equals log 10 of x minus 1. In this case, because we've shifted this graph down, this 1, 0, I'm just going to refer to the point. So the 1, 0, that intercept will now shift that down by 1. That's going to become 1, negative 1. And then we can sketch our graph going through that point. So again, we've just shifted it vertically down by 1 unit. The asymptote would still be at x equals 0 because we can see that in the argument, it's just x by itself. If we were to shift it up, so let's say we had y equals log 10 of x plus 1, the same situation. However, we're just shifting in the positive direction. So 1, 0, adding 1 to that y coordinate of 0 becomes 1, 1. And now would sketch our graph. The difference really between your x-axis translation and your y-axis translation is that your x-axis translation will affect where your asymptote is, so your vertical asymptote. The translation in the y-axis will affect where your x-axis intercept is. So let's have a look at this worked example. So sketch the graph of f of x equals log 2 of x plus 1 minus 2. Label all key features on the set of axes below. So generally speaking, when they're asking for all key features, they're asymptotes and intercepts, or all relevant intercepts, that is. So let's first start looking at our asymptote. That's the first thing I like to look at. So in this case, we can see we have a vertical asymptote at x equals -1, x equals -1. So it's being translated left by 1 unit. There's no reflections, so we know sort of that general shape is going to look something like so. We don't exactly know where our intercepts are at the moment, so we have to find those first, just in case our y-axis intercept is positive or negative, and same for our x-axis intercept. So we don't actually know where they are. We do know the general shape, and we do know we are going to have x and y intercepts. So let's solve for that. So x-intercept, we let y equals 0. So we're going to have 0 equals log 2 of x plus 1 minus 2. Now we're going to add 2 to both sides. So we're going to have 2 equals log 2 of x plus 1. Raise both sides to a power of 2. So 2 squared is 4 equals x plus 1. So x equals 3, that's 1. X equals 3 would be over here. So 3 comma 0. Considering we have a positive x-axis intercept, we know now we're going to have a negative y-axis intercept. But again, let's just solve that so you can find the exact value that it would be. Y equals log 2 of 1 minus 2. Anything with an argument of 1 becomes 0, so log 2 of 1 just becomes 0. So it's just going to be 0 minus 2, which equals -2. So the y-axis intercept here would be at 0, -2, 0, -2. So that's sketching the graph of f of x equals log 2 of x plus 1 minus 2. So again, the vertical asymptote at x equals -1, and it's been shifted down by 2 units. Domain and range of logarithmic functions. So the domain of a logarithmic function is dependent upon the asymptote and whether there is a reflection in the x-axis. To find the domain of the logarithmic function, we can solve the inequality that is x minus h, so the argument, to be greater than 0, for the function log a of x minus h. On the other hand, for the range of a logarithmic function is simply just r, or all real numbers, or you can write it as -infinity to infinity for as long as you have exclusive brackets, so curved brackets. The only time the range is different for a logarithmic function is if the question or problem specifies a certain domain. So that means you have to substitute in the endpoints of your domain to see when or what value they give you in the y-axis. So in this case, you may need to evaluate and consider those endpoints. It could be a practical problem, or it could just be a sketching of the graph where they've specified a certain domain. So let's look at this example. State the domain and range of f of x equals log 2 of x plus 2. What we can notice is that we have we have the vertical asymptote at x equals -2. So I'm not going to worry about where the exact x and y intercepts are in this instance, but what I will notice is that there are no reflections. So the general shape of this graph is going to look like so. It's going up towards the right. So if we're looking at the domain, we want to ask ourselves, where does x exist? So basically x exists in the horizontal direction where x is greater than -2. So x will be an element of curved bracket -2 to infinity. Again, it's not inclusive because there's an asymptote at that point, so we cannot use a square bracket, we have to use a curved bracket. Another way you could write that is just x is greater than -2. Both of those are perfectly correct. Looking at the range, we can see there's no restriction, so therefore our range is just going to be equal to all real numbers. So f of x is an element of all real numbers. Or you can also write -infinity to positive infinity. So let f be defined for all real numbers except 2, where f of x equals 2 log e of 2 minus x minus 2. There are a lot of 2's in this question. On the axis below, sketch the graph of f, clearly indicating axis intercepts and relevant asymptote. So in this case, logarithm, we're only going to have one asymptote. So let's have a look at what this graph now looks like. So first things first, we're going to look for our vertical asymptote. So vertical asymptote, we're going to have 2 minus x is equal to 0. Negative x equals -2. Therefore, x equals 2. So that's where our asymptote will be. There is a reflection in the y-axis because there's a negative x. So I know we're going to go towards the left, and it's being shifted down by 2. So I know generally the shape will look something like so. However, I don't know exactly where those intercepts are. So what we're going to do is solve for them. So I still call this part A. So x int, we're going to let y equals 0, or let f of x equals 0. So 0 equals 2 log e of 2 minus x minus 2. Add 2, so 2 equals 2 log e of 2 minus x. Divide both sides by 2, so we get 1 equals log e of, log e of 2 minus x. Raise both sides to a base of e, so e to the power of 1 is just e, equals 2 minus x. negative x equals e minus 2, which is approximately 0.7. So therefore x equals 2 minus e. So leave it in exact value. So yes, we know it's now, if e minus 2 is approximately 0.7, 2 minus e should be approximately negative 0.7. So at least we know it's in the negative direction. So it should be close to here. So it's going to be 2 minus e comma 0. So again, over time, you'll become more familiar with the approximations of e and logs, or base e of logarithms, I should say. We'll let x equal 0. So we're going to have f of 0 equals 2 log e of 2 minus 2. Log e of 2 will be less than 1, so let's assume it's less than 1, so it's going to be negative. That's just going to be, we can't simplify that any further, so that's just what it is. We know, why do I say we know it's negative? So log e of 2, that has to be less than 1. So let's assume that it's like 0.8. Okay, I don't know exactly what it is, but let's assume. So 2 times 0.8 is 1.6. 1.6 minus 2 is negative 0.4, so it has to be negative. So again, it doesn't matter about the exact value in this instance, or the exact approximation, I should say. We're only, whenever we have something where we have a base of e and a logarithm, we want to label, particularly if it's exam 1, we want to label our intercepts in exact value form. Okay, so rather than approximating is only good to know roughly where to put our points. However, in this case, we can just put it in exact value, or leave our answer as exact value, I should say. So in this case, that's going to be somewhere here. So 0, 2 log e of 2 minus 2. So now the domain and range of this function, so again, we can see that because of the reflection, x never passes 2. So this is for part B. So our domain will be where x is less than 2. And our range, again, because there is no restriction on the domain, our range will just be where f of x is an element of all real numbers. So now in this mega question activity, we're going to be looking to put all of this together, or everything that we've learned together. So the function f of x equals negative 2 log base 3 of x plus 4, where x is between negative 4 and 5, has a range of. So I hope that your answer was D, negative infinity to negative 4. To answer this question, I'm going to sketch the graphs just to make it easier for us to see exactly what is happening, and particularly because we have a domain restriction that I was talking about in earlier slides. So negative 2 log 3 of x plus 4, first thing I want to do is look for my vertical asymptote. Our vertical asymptote would be at negative 4. X equals negative 4 as our vertical asymptote. There's a reflection in the x-axis, so it's going to be coming down toward the right. And what we're going to do now is find our x and y intercepts. So x-intercepts, we let y equals 0, or let f of x equals 0. So we get 0 equals negative 2 log 3 of x plus 4. Divide both sides by negative 2. So it's just going to be 0 equals log 3 of x plus 4. 3 to the power of 0 is 1. So 1 equals x plus 4. Therefore, x equals negative 3. So it'll be negative 3, 0. And our y-intercept now. So y-intercepts, let x equals 0. So we can have negative 2 log 3 of 4. So because 4 is greater than 3, we know that's going to be greater than 1. Because the reason I say that is log 3 of 3 is 1. So log 3 of 4 has to be bigger than 1. So that means negative 2 times log 3 of 4 has to be a little bit greater than negative 2. So let's assume that it's there. So we're going to have 0, negative 2 log 3 of 4. So in this case, we can see that we're looking for our range. So normally this range would just be all real numbers. However, because we do have a domain restriction, we also have to take this into account. So when x is negative 4, we can see there's an asymptote there. So therefore, we will see that the range of at x equals negative 4 will be infinity, or positive infinity that is. However, now we have to consider x when x is 5. So let's substitute in x equals 5. So f of 5 would be equal to negative 2 log 3 of 5 plus 4, which is equal to negative 2 log 3 of 9. Log 3 of 9 can be rewritten as negative 2 log 3 of 3 squared. Using the plug law, we can bring that 2 to the front. So it becomes negative 4 log 3 of 3. We know log 3 of 3 becomes 1, so this would equal negative 4. There's an open circle at that point because we have curved brackets. Our range would be, in fact, negative 4 to positive infinity. So when we're sketching logarithms, we know the general form of logarithm is f of x equals a log e of x minus h plus k. And some of the important parts is that the dilation in the y-axis, the translation in the x-axis, and the translation in the y-axis. So information you need when you're sketching logarithmic functions, firstly you need the equation of the vertical asymptote. Then you need your actual intercepts, and then you need to consider any relevant transformations and in particular you need to consider those reflections. This will then obviously impact your domain and range, particularly if your domain has been restricted. So what's coming next? We have applications of exponential and logarithmic functions. So real-life applications. So exponential and logarithmic functions can be used in a variety of ways in real life, and in particular, as we've looked at in the past, they can be used in laboratories for when you're conducting experiments, or particularly when looking at exponential growth or decay. And for logarithms, they can also be used in music and Richter scale calculations. In this lesson, we're going to be looking at the applications of exponential and logarithmic functions. In particular, we'll be looking at exponential models and their applications, as well as logarithmic models and their applications. So firstly, we're going to look at exponential models. So when we're using exponential functions to model real-life events, we're generally going to be using something of the form a equals a naught times b to the power of t. So a naught is your initial quantity, and b is a positive constant. So it's something that where b, if could be if it's greater than 1, it's representing growth. If it's between 0 and 1, could be representing decay. So looking at exponential growth, as I mentioned, if b is greater than 1, the model represents exponential growth. So this could model situations such as population growth or compound interest investments when you're looking at financial applications. If b is less than 1, the model could represent exponential or natural decay. So I said 0 to 1 is generally when it's decaying. However, also when it's less than 1, if it's negative, that could also represent decay. Just the rate of change is slightly different. So this can also model situations such as radioactive decay, as well as cooling of materials. So looking at a worked example, we have a biological culture contains 100,000 bacteria at 8 a.m. on Tuesday. If the culture continues to grow at a rate of 8% per hour, at what time will the culture exceed 500,000? So write your answer correct to the nearest minute. Let's start with all of our working out. So we're going to have n. I'm going to let n be for our culture. And we're going to have a naught. So because we're saying it's increasing at a rate of 8% per hour, we know that b has to essentially be equal to this value. So b won't just be 8%. Because it's growing, it has to be 8% more than 100%. So we would have normally 1 plus r over 100 to the power of t. So in this 1 plus r over 100, that's equivalent to our b times 1 plus 8 over 100. And we're looking at to the power of t. It says if the culture grows at this 8% per hour, so t is per hour, at what time will the culture exceed 500,000? So we want to find t when n is equal to 500,000. So we're going to have 500,000 equals 100,000 times 1.08 to the power of t. We're going to divide both sides by 100,000. So we're going to have 5 equals 1.08 to the power of t. Take log base of 1.08 of both sides. So you get log base 1.08 of 5 equals t. In this case, because it says write your answer correct to the nearest minute, we do have to use a CAS in order to approximate what is log of 1.08 of 5. So now to approximate this value, we're going to have a log of 1.08 of 5. Press enter. So it comes to 20.91. So t was in hours. So it's 20.9124 hours. We can sort of disregard the 20 for now. We're going to know it's going to be 20 hours. Because the question's asking for to the nearest minute, we have to multiply 0.9124 by 60. So it comes to 54.744. And therefore rounding that up to the nearest whole minute would give us 55. So t equals 20 hours and 55 minutes. And because it's asking at what time, so we have to see it's 20 hours and 55 minutes later after 8 a.m. So it's going to be 4:55 a.m. on Wednesday, so the following day. So again, first you want to set up your exponential model and then refer to the question in terms of what it's asking for. So in this case, looking for the time or the exact time to the nearest minute. Now we'll look at logarithmic models. So where do log scales get used? There's a range of log scales that you may have already come across. Some of the most common ones include acoustics in the measure of loudness, Richter scale in the measure of earthquakes, octaves in music, as well as the pH scale. The standard form of a logarithmic model, you may recall from previous lessons, a logarithmic function can be modeled by f of x equals a log base b of x minus h plus k. Depending on the function that we want to model, this will affect the way in which the function is transformed. Again, we'll look at some of these in upcoming examples. So in this worked example, we're going to be looking at octaves in music. So octaves in music can be measured in cents, so n denotes cents. The frequency of two notes, f1, frequency 1, and frequency 2 are related by the function n equals 1200 times log base 10 of f2 divided by f1. In this instance, Jordan plays the piano and wants to calculate the number of cents between two Cs, where the middle C has a frequency of 256 Hz, and the C, an octave higher, has a frequency of 512 Hz. So in this case, we want to find the number of cents between these two Cs. First thing we want to do is the lower of the Cs. Where are we? It's the middle C. So the first one we're going to have is n equals 1200 log 10 of 512 divided by the frequency of the octave lower is 256. So 512 divided by 256 is 2. So we're going to have n equals 1200 log 10 of 2. And again, if the answer was exact value, you would leave it like that. However, in this case, let's find an approximate solution. If in the answer they wanted for us to leave as an exact value, this is how we would leave it. However, if we want to approximate, we would have to use our CAS. So now let's put in 1200 log 10 of 2 to get an approximate answer. So it comes to 361.236. So n equals 361.236. If we go to the nearest cent, that would just be n is equal to 361. So in this mega question activity, we're going to look to put everything together that we've learned throughout this lesson. So in this instance, we have the population of species A can be modeled by the linear equation 10,000 minus 200t, and the population of species B can be modeled by the exponential equation 8,000 plus 4 times 2t. So we can see that the value for t and the population size of each species, when they're equal, is... So I hope that you found that t is equal to 7.15 and n is equal to 8,570. So in this instance, we have a linear equation and an exponential equation. We want to find when they are equal. So that is, we're going to set up a simultaneous equation. Okay, so we're going to have 10,000 minus 200t is equal to 8,000 plus 4 times 2 to the t. Okay, so again, in this instance, we just want to we could put this directly into our CAS, but let's show a little bit of working out first. So subtract 8,000 from both sides, we're going to have 2,000 minus 200t is equal to 4 times 2 to the power of t. Let's divide both sides by 4. So this is going to become 500 minus 50t is equal to 2t, 2 to the power of t. If you want, you can factorize the left-hand side. You don't have to, but let's do it anyway. Why not? Doesn't hurt. Taking a common factor of 50, so we're left with 10 minus t is equal to 2 to the power of t. So therefore, 50 is equal to 2 to the power of t on 10 minus t. And now we can put this into our CAS to solve. So we can go solve 50 equals 2 to the t on 10 minus t, t. So just write out what you're going to put into our CAS. Now let's actually put it into our CAS to find out what the value for t is. So we're going to menu algebra solve. So we're going to have 50 is equal to 2 to the power of t divided by 10 minus t, t. So t is equal to 7.1532. So we can see that in our solution, we have t is equal to 7.15. So let's use that value to 2 decimal places. So t is equal to 7.15. So now that we've found the value for t, obviously we can see that our solution is in fact a, because that's the only one with t equals 7.15. However, let's just confirm we do get the n value, or the population size, of 8,570. To find that, we need to substitute in a t equals 7.15 into one of our equations. I'm going to sub into the linear equation just because it's a little bit easier to do. Let's substitute that into the NA of t is equal to 10,000 minus 200 times 7.15. And again, we can put this into our CAS to confirm. So we're going to have 10,000 minus 200 times 7.15. We enter, and we end up with 8,570. So therefore, n of 7.15 is equal to 8,570. So when these two populations are equal, it will occur after 7.15 years, and the population size of each of these species would be 8,570. So in summary, with exponential and logarithmic models, firstly, with exponential models, we have a equals a naught times b to the power of t. So a naught being that initial quantity. For the most part, you will be given initial population sizes, whether it be of a species or a bacteria or something similar. And finally, b is a constant, so it may be positive. If it is greater than 1, it's growth. If it's between 0 and 1, it's decaying. So it's always good to remember how your graph or how your model will work. For logarithmic models, again, the standard form of a logarithm, a log base b of x minus h plus k. Keep in mind the shape of the graph and any reflections as well, and use all the relevant information to find those values of a, h, and k. So finally, when working with each of the models, you want to find the value of the unknown variables in each of those models and then calculate or evaluate that model based on the problem. In our next lesson, we're going to be looking at the inverse relationship between exponentials and logarithmic functions. So hopefully by now you know what is the common difference between bacteria and logs, and you've seen this in one of the previous lessons. But if you haven't or you can't recall what that is, essentially the common difference between bacteria and logarithms is that bacteria grows exponentially, whereas logs, in this case, don't actually grow logarithmically. However, they do, in this instance, they are resembling a logarithmic function, and they are actually the inverse of one another. So in this lesson, we're going to be looking at the inverse relationship between exponential and logarithmic functions. So we'll be finding the inverse of these two functions, using inverse functions to solve equations, and finally solving equations where we have an exponential and a logarithm on each side of the equation. So hopefully by now you know what is the common difference between bacteria and logs, and you've seen this in one of the previous lessons. But if you haven't or you can't recall what that is, essentially the common difference between bacteria and logarithms is that bacteria grows exponentially, whereas logs, in this case, don't actually grow logarithmically. However, they do, in this instance, they are resembling a logarithmic function, and they are actually the inverse of one another. So in this lesson, we're going to be looking at the inverse relationship between exponential and logarithmic functions. So we'll be finding the inverse of these two functions, using inverse functions to solve equations, and finally solving equations where we have an exponential and a logarithm on each side of the equation. So the inverse of exponential and logarithmic functions. So finding the inverse of an exponential and logarithm is very similar to when we would find an inverse of any other function. That is, we reflected about the line y equal x. So to find the inverse function, should it exist, we let x equal y and rearrange for the inverse of x. So in this instance, let f of x equal e to the power of x, so an exponential function. We can see that ex equals e to the power of y, and therefore taking log e of both sides, we're left with the inverse is equal to log e of x. So hence, if g of x equals log e of x, then the inverse of that would also equal e to the x. And we can sort of see this graphically as well. So let's say we had an exponential function, so that's y equals e to the x, and that's an intercept at 0, 1. And now we have our logarithmic function, I should say. If I draw that one nicely. So that's y equals log e of x, and then we also have our line that we reflect about, the line y equals x. So we can see that the exponential function y equals e to the x is in fact the inverse of log e of x, and vice versa. Log e of x is the inverse of the exponential function e to the x. So in this worked example, we're going to be looking at the function f being defined by all real numbers, where f of x is equal to 3 e to the power of 2x minus 1. Find the rule of the inverse. So in part A, we're going to be looking at finding the rule of the inverse function. So when we're looking at inverse functions, we want to essentially swap our x and y. So let x equal y. So therefore we have x equals 3e to the 2y minus 1. Now we'll just solve essentially for y. So add 1 to both sides. So it's x plus 1 equals 3e to the 2y. Divide both sides by 3. So x plus 1 divided by 3 equals e to the 2y. To undo that exponential, we take the log e of both sides. So therefore we're going to have 2y equals log e of x plus 1 over 3. And finally, dividing both sides by 2, we have y equals a half log e of x plus 1 on 3. And just to rewrite it using the correct notation, so f negative 1 of x is equal to half log e of x plus 1 all over 3. So that's our inverse function of that f of x equals 3e to the 2x minus 1. In part B, we're going to find the domain of the inverse function. So in this instance, the domain of the inverse function is always equal to the range of the original. So if we look at the original function, 3e to the 2x, I'm just going to quickly sketch what that graph may look like. What we notice is the negative 1 means we have a horizontal asymptote at negative 1. So 3e to the 2x, it's growing, so it might be like something like so. And therefore we can see that the range of f of x is where f of x is an element of negative 1 to infinity. So the range of f of x is where f of x is an element of negative 1 to infinity. So that means the domain of the inverse, so the domain of f1 of x, is where x is an element of negative 1 to infinity. So if you really wanted to, you could find the asymptotes for the inverse as well. That is perfectly fine. So if we were to do that, just for clarification's sake, we would always let the argument equal 0. So we're going to have x plus 1 on 3, because that's the argument. So that's come from there. Equals to 0. Multiply both sides by 3. We're left with x plus 1 equals 0. And therefore our asymptote is in fact at x equals negative 1. There are no reflections. It's essentially going in the positive direction. So it's going to be negative 1 to infinity. So again, you can use that note of, well, the domain of the inverse is equal to the range of the original. Or you can also, because you have a logarithmic function, you can actually find where the asymptote is and refer to the presence of any reflections. So a bit of a teacher's tip. So the domain of an inverse function is equal to the range of the original. And the opposite is true. So the range of an inverse function is equal to the domain of the original. So it's something really worthwhile knowing, not just for exponential logarithms, but all inverse functions. So using inverse functions to solve equations. So solving exponential and logarithmic equations using the inverse. So as you may recall, when converting from an exponential function, we take the logarithm of both sides. So for instance, if we had a to the x equals y, we'll take log base of a of both sides, and we're left with x equals log a of y. When we convert from a logarithm, we raise both sides to that base of that logarithm. So log a of x equals p. We have a to the log a of x equals a to the p, because we have the base of a in the logarithm. And finally, we're left with x equals a to the p. So if we look at the example, solve log 2 of 2x minus 3 plus 1 equals 0. So first we're going to subtract 1. So we're going to have log 2 of 2x minus 3 is equal to negative 1. Raise both sides to a power of 2 to the base of 2. So it's going to become 2x minus 3 is equal to 2 to the power of negative 1. 2 to the power of negative 1 can be rewritten as a half. So we're left with 2x minus 3 is equal to a half. Add 3 to both sides. We're left with 2x equals 3.5 converts to 7 over 2. And finally, we're going to divide both sides by 2. So we're left with x equals 7 over 4. So really the key part was here when we're converting from a logarithmic form to exponential form to then evaluate that right-hand side. And obviously get our argument as a linear equation. Solving equations where f of x is equal to the inverse. Essentially what this does is you're finding the intersection between the original graph and the inverse of this particular graph. So when finding the value or values, again, you can have multiple intersection points depending how your graphs are translated. It is important to recall that the inverse function has been simply reflected about the line y equals x. So from this graph, we can see if a function is to intersect with its inverse, it will actually occur on the line y equals x. So yes, you can essentially solve in your CAS f of x equals the inverse and off you go. However, you can also solve just f of x equals x or x equals your inverse because it has to occur on the line y equals x. This is true for all inverse functions, again, not just exponential logarithms. It's really useful for when you're solving particularly square root graphs and parabolas and other functions where you can actually solve by letting it equal to x rather than trying to solve two different types of functions as well. Or what I mean by two different types of functions is that they're two functions that it's really hard to sort of solve together. So again, you can use the notion that if they do intersect, if a function and its inverse do intersect, it will occur on the line y equals x. In this example, we're going to find the points of intersection, or all points of intersection between the graph of f of x equals log e of 2x plus 1 and its inverse. So to go about this question, the first thing we want to do is in fact find the inverse equation, or inverse function, I should say. And what we're going to do is first swap or let x equal y. So let x equal y. So therefore we're going to have x equals log e of 2y plus 1. I'll take base e of both sides, so it's going to become e to the x equals 2y plus 1. Subtract 1, so we're going to e to the x minus 1 equals 2y. And finally, dividing both sides by 2, we're left with y equals e to the x minus 1, all divided by 2. And to put it into proper notation, we have f of an e to 1 of x is equal to e to the x minus 1 over 2. Because we want to find the point of intersection now, basically we want to make simultaneous equations, we want to equate them. So we're going to have log e of 2x plus 1 is equal to e to the x minus 1 over 2. So now we can go and solve this on our CAD. So normally you could solve this using menu algebra solve as you normally would solve any sort of equation. However, I do want to show you how to do it graphically. So by finding the point of intersection or points of intersection on the CAS, but using the graph. So for at home, we want to go to our graph, and then we're going to type in both of our functions. So we're going to have our original function, which was log e of 2x plus 1. So control log e, where are you? There you are, 2x plus 1, and then press enter. Then now we want to also now put in our inverse function, so it's e to the x. There we go. So in fact, if you notice, we actually have 2 points of intersection, so it's always good to double check. And when you do menu algebra solve, you may get 2 x values, and then obviously we want to find the corresponding y values. But as we mentioned before, they should both be the same because it always occurs on the line y equals x. So the x value should equal your y value at that corresponding value. And let's see this on the graph. So if we go menu, analyze graph, we want to find the intersection. So this dotted line will come up. So we just want to click anywhere that it might be. And then finally cover our points of intersection. So the first point of intersection we can see is 0, 0. Then let's do it again. So we're going to go menu, analyze graph, intersection. And we're going to do that second point up there. And in fact, the second solution is 1.26. So x equals 0 and x equals 1.26. And their corresponding y values are y equals 0 and y equals 1.26. The points of intersection at 0, 0 and 1.26, 1.26. So in this mega question activity, we're looking to put it all together, and this one is fairly common to see on the end of year exam. It was actually in the 2013 VCA exam 2 multiple choice section. So we have part of the graph of y equals f of x, where f is defined for all real values, and f of x is equal to 3 minus e to the x is shown to the right. Which of the following could be the graph of its inverse? So I hope that you answered A. So again, you could do this graphically and have a look at what it may be. However, I always like to find the actual inverse equation first and see which of these graphs it would match. To do this, let's first swap out x and y. So we're going to have x is equal to 3 minus e to the y. Subtract 3 from both sides, so we have x minus 3 equals negative e to the y. Divide both sides by negative 1. So we're going to have 3 minus x equals e to the y. And then finally take log e of both sides. So we have y equals log e of 3 minus x. And what we can see, there's been a reflection. So it's going to the left. And instead of being b would be if we just had log e of x minus 3. But because we have log e of 3 minus x, there is a vertical asymptote at x equals 3, and it's going to the left of the screen. So it's essentially being reflected about that y-axis, or about that asymptote at x equals 3, and therefore the solution is A. So in summary, inverse of exponential and logarithms, again, you're swapping your x and y, you're finding the inverse functions the exact same way as you would find it for other functions. Domain and range of inverse functions, again, it's important to recall the domain of the inverse is equal to the range of the original, and the range of the inverse is equal to the domain of the original. Points of intersection between the original and its inverse. So if the function and its inverse are to intersect, they will intersect on the line y equals x. Again, this is due to the notion that the inverse is just a reflection of the original about the line y equals x. And finally, using the CAS to find the points of intersection. So obviously we can use our CAS by using solve. However, you can also find these points of intersection graphically on your CAS by going menu, analyze graph, and then finding your points of intersection that way as well. So this comes to the end of our sort of content, if you like, for chapter 6, and what's coming next is our chapter check.